Okay, for today's video, I want to talk about the static failure theories, the distortion energy theory, and maximum shear stress theory. The reasoning behind having these static failure theories is that quite often we have a combined stress situation, and we want to compare it to the only information that we have on the material, that being from an axial pull test, which gives us either a yield strength or an ultimate strength right here. All right, this is on a stress strain curve, you remember from Matt Tsai. All right, one of the ways that we could try to take our combined stress scenario and compare it to this axial test is to take the principal stresses. So if we made a graph where we had the principal stress, the first principal stress, and divide it by the yield strength right here, so that we have like a safety factor of 1. And we did the same thing for the second principal stress, and we got that safety factor of 1. We could make a boundary, all right, in this graph and say if our calculated stress ends up within this boundary, we're going to be safe. If it's outside this boundary, it's going to fail, right? The simplest case is if you just take a look at the first principal stress and it's greater than 1 right here. If it were to land right there, you would say, okay, that makes sense. It's going to be greater than the yield strength, therefore it's going to fail. But in reality, when parts that are under combined stress were measured and actually found when they failed, we'd find that down here in this lower quadrant that things would fail even though they fell inside the box. Up here in this upper quadrant, things would be able to withstand higher stress than the box would predict. So that's what the theories are there to try to address. The first one I'll describe very shortly. It's the easiest one to calculate, maybe not the easiest one for me to explain, but I'll say that easiest way to picture it is to look at the graph and say, hey, we could draw lines that are right here between these two, and we could say, oh, now this new boundary will predict an envelope within which, if you calculate stress and it's within that boundary, you're going to predict that it's going to be okay. The way that it ends up mathematically working, right, is pretty straightforward, more straightforward than this graph would predict. What we try to find here is when we calculate the stress situation for a piece, we find the principal stresses in Moore's circle here, and this maximum shear stress theory, we're going to find the maximum shear, the absolute maximum shear stress is going to be up here, as we've described earlier. Now, we want to do an apples to apples comparison. What if we have a pull test, right, is going to have stress in only one direction? So the Moore circle of that is really just going to be a point here, right? That's going to be this stress that was applied, yield strength, and on this side is going to be 0, right? So the Moore circle for that one is going to look like this, and its maximum shear strength right here is going to be this right here. So that's going to be like the yielding shear strength. It's good. So if this right here is the yield strength, then this there's going to be an equivalent, or not an equivalent, but there's going to be, I shouldn't write that way, I should write it this way with a little s. This is the yield strength. It's going to be 1/2 of the yield strength right here. So this is the yield strength. This is going to be obviously 1/2 of that yield strength. So when we want to find a safety factor, then we'll do a subscript of the maximum shear stress theory, MSST, is going to be the absolute maximum. We don't always have to write it this way, but I want to emphasize it. Stress that we calculate divided by the shear strength, all right, which we could also say, and we'll just go ahead and write that. I'll write it again, and we could say that it's going to be 1/2 the yield strength right there. So that's the maximum shear stress theory right here. That's how you calculate what the safety factor is predicted by that theory. Now, the next one, and this is the most common, the most widely used, is distortion energy theory. It's also known as von Mises, and when we calculate, we get von Mises stress. I'll go through this relatively fast because there's a lot of math involved. But the idea is that when you observe a hydrostatic stress, that is a stress that's equal on every side of a piece, it can withstand a whole lot more stress in just one direction or in some off non-balanced direction. So you could say that, hey, there's something happening here with this hydrostatic stress. We could kind of like, with that defined, we could say that, hey, the other kind of stress that's happening is the distortion stress. But the best way to try to calculate these things, or to try to get to the bottom of what's going on, is to look at the strain energy that's being imparted onto the specimen. And so you could break the total amount of strain energy that's happening onto anything into this hydrostatic energy and distortion energy. All right, so the strain energy is divided that way into these two things. You can think of the distortion energy as the energy that's imparted on something because it got twisted and deformed angularly out of place, whereas the hydrostatic one is just something that changes the volume of the piece. And the theory here is that yielding of something is primarily affected by that distortion energy. The energy that changes the volume of it isn't really as big of a concern. So first off, I'm going to talk quickly about what is strain energy. One way of thinking about it, I think this is an easier way to describe it, is you could look, we're going to calculate strain energy per unit volume. We know that volume is area times length. We know that stress is force divided by area, and strain is displacement divided by length, right? So if you had a piece like this right here, and you had that area on it, and you had a length right here, so this is the area, and you applied a force to it, it would deform a certain amount, and that would be right here, this. And you know that energy is going to be force times displacement. If you multiplied the stress times the strain, right, the stress times the strain, you would end up with, if you look at the top, force times displacement, so you end up with energy. If you look at the bottom of area times length, you end up with volume. So you end up with this thing that we could call strain energy, right? And as a practical matter, strain energy is the area underneath the stress-strain curve. And if you look in other subjects, you'll often find that the area underneath the curve is going to be some type of energy thing. You could find it in different examples. Now also, this is going to be a triangle of the area underneath this curve, so we need this 1/2. You would also find that 1/2 if we were to integrate with one parameter versus another to be able to find it, little increments. We would find that it's 1/2. So we know that the area underneath the curve is the strain energy. The total strain energy, therefore, is going to be all these principal stresses times the principal strains, right? And the 1/2 is, of course, what you saw from the underneath the graph. If we transform the principal strains into principal stresses by way of Hooke's law, we could, with Poisson's ratio, riding along because this is a three-dimensional strains and three-dimensional principal stresses you have to look at. We could come up and substitute these back up into here and find this big, long, nasty equation. And with that big, nasty equation, we could also say, hey, let's try to find the hydrostatic, right? This up here was the total right here. And now we want to find the hydrostatic stress. We could substitute in an average stress for everywhere we found, and we could collect the terms, and we would find that the hydrostatic stress was equal to this calculation. And also now we could make another little mathematical thing. We collected it up here. We could redistribute it down here. We could say that, hey, the average stress we also know is going to be those three principal stresses divided by 3. So we're going to stick that back in here. It's squared, and now we're going to have this big ugly mess down here. That's the hydrostatic stress. Well, let's go back to this equation up here where we said that the total stress, the total strain energy was going to be that hydrostatic plus the distortion. But it's the distortion energy we want to find. So we take the total and subtract the hydrostatic. All right, so if we do that, take the total and the hydrostatic, okay, these were from the previous couple slides, and we just subtract those two and do some factoring, we find that this is the distortion energy. Now, the theory basically was that the distortion energy is the only thing that matters. So we want to compare the distortion energy that we calculate to the distortion energy that happens in a pull test. We're going to say that when those two things are equal, that's when we're going to predict failure. So in the pull test, we could substitute, hey, we know that both in the out of plane directions are going to be zero, that the only in one direction is going to have stress, and that's going to be equal to the yield strength. So we can have the test distortion energy is going to end up being equal to this. So when these two things equal each other, that's going to be when we find failure, right? So there's a little bit of math involved, but this guy down here, when that equals this right here, that's when we predict failure. Doing a little bit more massaging, we say that, okay, here is the principal stresses all put together, and when that thing is greater than or equal to yield strength, that we're going to find failure. These are also, by the way, also known as octahedral stress and shear energy theory, von Mises, the von Mises-Henke. But in terms of the graph that we previously saw, you could see that the dotted line here is the maximum shear stress theory, which is also called Tresca. That's another name for it. Instead, the distortion energy theory, the von Mises stress, or the limit right here, it matches a lot more closely to the experimental results in all these quadrants right here. That's one reason for using it. Another is that it's a lot easier to visualize when you're using finite element analysis. So that's the idea behind the distortion energy theory. This equation might be a little ugly, a little too much when looking at it, a little overwhelming. Just the ones that you're going to find that you use the most, as long as you have to make sure that you're in the situation that they're applicable. You can use the principal stress if you have plane stress. If you only have two principal stresses, that is, one of the principal stresses is going to be equal to zero. The two non-zero ones, you can find the von Mises stress that's always given with a sigma and an apostrophe. You can find it from this equation, or hey, you don't have to find the principal stresses even, because when you have that scenario, you could just input the x and the y from, make sure that it's the x and the y direction. It could be the z direction, the x and the z direction, just as long as the y in that scenario was zero. You can use these two equations. And an even simpler scenario is when you have just, and by the way, I also should have put a shear stress on there. If you have a scenario where you only have normal stress in one direction, right? It's the only time you can do it, and you also have shear applied, but you have normal stress in only one direction, you can use this simplified version. And by the way, this is probably the one that you'll use the most often. You just need to remember that it's only when you have this scenario. All right, so that's a description of the failure theories, and you can refer back to this video, hopefully, if you forget, like, why are we doing this?